My apologies, but when you come across this video, it's time to say goodnight to your phone. Because over the next 1 hour, you will witness how a black hole devours all information using just 3 numbers. You will feel the quantum boiling of Hawking radiation at the edge of the universe, until all stars fall into the eternal darkness of entropy, finally seeing the universe's simplest, yet most profound, ultimate mystery. May this journey through a black hole open a window to the starry sky for your weary soul. How many numbers do we need to describe the moon? The lunar surface is covered with craters of various shapes, marks left by countless asteroid impacts over billions of years. If a similar exomoon orbited another terrestrial exoplanet, even with a similar appearance, its crater distribution pattern would be entirely different. To accurately describe the features of each moon, we would need to assign latitude and longitude coordinates to thousands of craters and record the size of each one. We would quickly find that even before discussing the chemical composition of the lunar surface and its variations, the required number of digits would skyrocket from thousands to millions, or even more. And this is just for one moon, one of the relatively simple objects in the universe. So, how many numbers are needed to describe a planet, a star, a nebula, or even the largest black hole in the entire universe? The answer might astound you. Just 3 numbers. No more, no less. On one hand, black holes exhibit a stunningly simple nature. Just 3 fundamental parameters are sufficient to classify them completely: mass, charge, and angular momentum. Mastering these 3 numbers is like holding a master key to the secrets of black holes. Yet, the paths to the birth of these mysterious celestial objects are incredibly diverse. Some black holes grow gradually over billions of years by greedily consuming surrounding gas and dust. Others are born from spectacular cosmic events, the dramatic collapse of massive stars in Type II supernova explosions. Still others might originate from repeated mergers of black holes, like a cosmic league of devourers. We can even imagine a bold scenario: a black hole made of all the knowledge of the Milky Way, containing the contents of every encyclopedia, every electronic database, carrying all the thoughts and data of human civilization. Regardless of how a black hole forms, regardless of how much information has fallen into it, once the black hole is formed, all this complex information is simplified into those 3 fundamental parameters. The origin and composition of the black hole seem to become irrelevant. This phenomenon itself is an almost unanswerable puzzle. The possibilities for forming a black hole are nearly infinite. So why can they be described by just 3 numbers? Where did all the vanished information go? Has the black hole truly forgotten its own origin? Or does this information exist in some hidden form we have yet to understand? What secrets are hidden inside a black hole? And what does it mean for the entire universe? In the 1780s, in the English countryside, the position of a clergyman, though not prominent, was quite comfortable. The job came not only with a spacious residence and a respectable salary, but also with a retinue of servants to manage daily affairs. Young assistant clergymen had the duty of providing spiritual comfort and visiting the sick, while also enjoying a leisurely life. For those with higher aspirations, this leisure provided precious time for contemplation and exploring the world. This was the life of Reverend John Michell in that era. At that time, Newton's theory of universal gravitation was like a brilliant star illuminating the entire scientific world. This great prophet revealed that gravity is a universal force. Any object with mass is instantaneously pulled towards every other object. Nothing can escape its grasp. Reverend Michell was not only immersed in thinking about the mysteries of gravity, but also turned his attention to the nature of light. Newton had proposed that light is composed of tiny particles called corpuscles. If this theory were true, and gravity were truly omnipresent, then these tiny light particles must also be affected by gravity. They would be pulled and drawn back. Michell knew that the speed of light was far beyond human imagination. As early as the 18th century, the astronomer James Bradley, with extraordinary wisdom, had accurately measured this cosmic constant by observing the subtle stellar aberration of light from distant stars as the Earth orbited the Sun. As the Earth moved in its orbit at tens of kilometers per second, the vector addition with the speed of light, though causing only a slight change, was enough to cause a measurable displacement in the apparent position of the stars in the sky. Thus, humanity learned that the speed of light is approximately 180,000 miles per second, approximately 300,000 kilometers per second. This was an astonishing speed, yet still not infinite. Michel's intuition told him that an object thrown upwards will eventually fall back down. However, if given enough initial velocity, this certainty could be broken. The object would escape Earth's gravitational pull and reach the vastness of space. This critical value is called the escape velocity, the minimum speed required for an object launched vertically to escape a planet's gravity and enter infinite space. Within the framework of Newtonian gravity, calculating the escape velocity of any planet is not difficult, as it is closely related to the celestial body's mass and density. The greater the mass and the higher the density, the greater the escape velocity. For example, the Moon requires only 2.4 kilometers per second to escape. The Earth needs 11.2 kilometers per second, Jupiter about 60 kilometers per second, and the Sun itself a staggering 617 kilometers per second. Let us imagine an even denser object. Michel proposed that if an object were dense enough, its escape velocity could exceed the speed of light, which is considered the ultimate speed limit. For such an object, light emitted from its surface would be unable to escape its grasp. In this scenario, the object would appear to have gravitational mass, but be completely black, as if shrouded in endless darkness. Even light would be captured by its powerful gravity, trapped within, unable to escape. It should be noted that the theories and arguments used here are based on Newtonian physics, which were later superseded by Einstein's theories. However, it is undeniable that the concept Michel described still exists and is clearly recognizable. Michel's work, though its actual name was not used for nearly 2 centuries, became the first description of what we now know as a black hole. It must be said that Michel was far ahead of his time. His research, at the time, seemed merely an abstract curiosity, like a pearl left in a corner. It was soon filed away in the drawers of scientific history, where it lay dormant for 150 years. The next time this drawer was opened was in the brutal trenches of World War I. German astronomer Karl Schwarzschild was desperate to escape the hellish environment around him. In that moment of life and death, he began to ponder Einstein's new equations of general relativity. 10 years after creating special relativity in 1905, Einstein, with extraordinary genius, extended this revolutionary theory to the domain of gravity, forging the scientific monument of general relativity. This theory, describing the mysteries of the universe, consisted of 10 exquisite equations. When it appeared, its complex mathematical form was as daunting as a labyrinth. In 1915, people did not know how to solve these equations. To tackle these problems, Schwarzschild sought the simplest solution he could imagine. He envisioned a space-time structure with spherical symmetry around a point mass. After substituting all the physical quantities into the equations and performing precise calculations, he arrived at a result of epoch-making significance, now known as the Schwarzschild solution. This solution not only became the most famous particular solution to Einstein's equations, but also revealed the profound connection between mass and space-time curvature in general relativity. Mass causes the surrounding space-time to deform, and the degree of this deformation changes with the distance from the center of mass. The closer to the center of mass, the more significant the space-time curvature. At a distance, this effect is almost negligible. The Schwarzschild solution contains a shocking physical property. There exists a critical distance. At this special position, known as the Schwarzschild radius, some terms in the equations suddenly become zero, while others tend towards infinity. This mathematical phenomenon predicted the existence of a peculiar type of celestial object in the universe, the black hole. Around a black hole, there is a spherical boundary called the event horizon. It acts like a one-way gate in the universe. Any matter that crosses this boundary will inevitably fall towards the center of the black hole. Outside this critical radius, an object could theoretically still escape the black hole's gravitational pull by traveling faster than light. But once inside the event horizon, even the fastest thing in the universe, light itself, is powerless to return. The laws of physics declare with irreversible authority that any astronaut attempting to escape or traverse the event horizon is on a one-way trip to the center of the black hole. Once that invisible boundary is crossed, the arrow of time points inexorably towards the black hole's core. As gravity tightens its invisible grip, the astronaut can only fall and fall until reaching the singularity, a point where even classical general relativity breaks down, where space-time curvature becomes infinitely twisted and the laws of physics collapse. This is just like Michel's earlier calculation. When the escape velocity exceeds the speed of light, any object is doomed. If a certain mass is compressed to a size smaller than its Schwarzschild radius, collapse is inevitable. Our Sun, if compressed to a diameter of about 3 kilometers, or the Earth, if shrunk to less than a centimeter, would form a black hole. A person's Schwarzschild radius is even smaller, on the order of 10⁻23 meters, tinier than an atomic nucleus. If all the matter in the Milky Way were compressed into a sphere with a radius of less than 0.2 light-years, a true supermassive black hole would be born. This mathematical solution that reveals the ultimate fate of the universe, the Schwarzschild radius, was born in 1915, at the glorious moment of Einstein's general relativity. However, similar to Michel's foresight half a century earlier, it was initially regarded merely as a product of theoretical physicists' curiosity. Unfortunately, as quantum mechanics swept through the world of physics in the 1920s, 30s, and 40s, revolutionizing many disciplines, scholars studying gravity and general relativity seemed to be in an academic backwater. American physicist Richard Feynman's comments at a gravity conference in the early 1960s profoundly reflected the academic view of the field at the time. He frankly stated, "I got nothing out of this conference. This field is dead because of the lack of experimental support. No top scholars are involved, so it's filled with a lot of mediocrities. It really raises my blood pressure." But the slump Feynman described in his sharp summary changed dramatically in the late 1960s. With the perfect combination of theoretical breakthroughs and observational progress, research into black holes and general relativity experienced a strong revival that continues to this day. In the public consciousness, the physicists nurtured by this scientific renaissance have an influence that even surpasses any other physics icon of the 20th century. Among them, Stephen Hawking holds a particularly special place. Born in 1942, this genius's extraordinary life inspired countless successors. His academic journey began with undergraduate studies in physics at Oxford University, followed by doctoral studies at Cambridge. But fate threw two bombshells at him during his studies. At the age of 21, he was diagnosed with degenerative amyotrophic lateral sclerosis, ALS, and doctors predicted he had only about 18 months to live. He unexpectedly graduated with first-class honors. Facing the encroaching shadow of death, Hawking showed amazing fighting spirit. He threw himself into his research, eager to leave an immortal achievement in his limited life. Fate ultimately smiled upon this fighter. He not only defied the doctor's predictions, but passed away at the age of 76, becoming a world-renowned scientific giant. And his great fame largely stems from the black hole research renaissance that occurred between 1967 and 1974. This scientific revolution not only reshaped the map of modern physics, but also forged an important chapter in Hawking's legendary life. Hawking, together with mathematician Roger Penrose, embarked on an extraordinary journey of scientific exploration. In this collaboration, they overturned the old cognitive framework in general relativity with their revolutionary wisdom. The two scientific giants jointly proved a set of landmark theorems. Imagine a physical picture where a group of massive particles approach each other, pulled together by gravity. Their ultimate fate seems shrouded in mist. Will they inevitably collapse to form a black hole, or will they scatter after bouncing off each other, escaping the clutches of gravity? Facing this unresolved physical problem, Hawking and Penrose, with their outstanding mathematical insight, gave a conclusive answer. Under fairly general physical conditions, a collection of matter dominated by gravity will eventually collapse. and the inevitable end of this process is a singularity wrapped in a black hole within the structure of space-time. This breakthrough discovery did not stem from intuition or subjective conjecture, but was the result of the two scientists' rigorous reasoning. They pioneered the use of Penrose diagrams, a revolutionary visualization tool that completely changed the way relativists perceive the nature of space-time. This innovative method not only simplified the complex structure of many solutions to Einstein's equations, but also provided humanity with the first clear framework for understanding the global impact of black holes. Through intuitive causal structure diagrams, the essence of space-time was presented with unprecedented clarity. In these exquisite diagrams, light rays always travel elegantly at a 45-degree angle, revealing the mysteries of the interwoven fabric of space-time, clearly delineating which points will exert a causal influence on others. The event horizon is like a mysterious intersection where, as a celestial body withers and transforms, it will eventually sever its causal link with the infinitely distant universe. Hawking's mind soared like a brilliant star. His imagination transcended the paradigms of space and time. We have every reason to believe that the peculiar celestial bodies depicted by these curves are by no means illusory. Black holes may indeed lurk in the deep recesses of galaxies. Fortunately, astronomical observation technology is innovating at an astonishing pace. Satellites have sent telescopes into space, allowing humanity to peer into the heavens from above the clouds for the first time, not only in the visible light spectrum, but also in other electromagnetic spectra, such as X-rays. This breakthrough brought a shocking discovery. The X-ray sky is much busier and more crowded than expected. Particularly noteworthy was an unusually bright and deadly radiation source, Cygnus X-1. Where did such dense, high-energy X-rays come from? And how could they erupt from such a tiny region? Only one perfect explanation could fit these observational data. There was a deadly black hole there. As matter accelerates and falls into the black hole, it emits these high-energy X-ray photons. Since scientists first discovered the existence of the black hole Cygnus X-1 in the 1970s, we have found many more black holes. Within the Milky Way alone, there may be as many as 100 million black holes lurking. In 2015, a landmark moment arrived. Humanity observed a black hole collision for the first time. This cataclysmic event in the cosmos produced gravitational waves, and the LIGO Observatory in the United States successfully captured this precious signal. But the enthusiasm for black holes during this period was not just due to the focus on astrophysical observations of galactic objects in offices, nor was it just a burst of inspiration while frantically writing long equations on a blackboard at night. The theoretical exploration of black holes had become a wonderful new stage for the most extreme problems in the universe. Here, scientists roamed freely, exploring the mysteries of the cosmos. To us, the human face is all too familiar. We can easily recognize its basic shape, yet it has almost infinite variations. The marks of age, the shade of skin, the color and style of hair, the sprinkle of freckles and moles, the expression of a smile, the whiteness of teeth, the freshness of skin. How many numbers and how much information would it take to describe any single human face with complete accuracy? In comparison, black holes seem strange and peculiar, but in a way, they are much simpler. This simplicity is clearly reflected in the solutions to Einstein's equations. Nevertheless, finding such solutions is no easy task. In 1915, shortly after Schwarzschild discovered the simplest black hole solution, another generalized solution was found, the Reissner-Nordstrom solution for a charged black hole. But it wasn't until nearly 50 years later, in 1963, that the most important generalization of the Schwarzschild solution appeared. This was the Kerr solution, named after the New Zealand relativist Roy Kerr. The Kerr solution also describes an uncharged black hole, but it depicts one with angular momentum, a black hole that can rotate on its own axis. Imagine a supermassive cosmic ballet dancer spinning rapidly, her extremely heavy arms outstretched. This ballerina's weight is almost at the threshold of forming a black hole, but her density is just a little bit off. When she retracts her arms to increase her rotation speed, her weight instantly exceeds the threshold density, and she collapses into a black hole. And this is a rotating black hole. The angular momentum she had before collapsing did not disappear. It seems to have been integrated into the black hole. This phenomenon is reflected in the Kerr solution. But what is puzzling is why there seem to be so few black hole solutions. There are only the Schwarzschild solution, the Kerr solution, and their generalizations. In fact, the limited number of black hole solutions is not due to a lack of effort by physicists. In their research, they first delved into the equations of general relativity and then considered what types of solutions would lead to the formation of black holes. Later research proved that these black holes have some unique features. The results of their solutions are now known as the black hole uniqueness theorems. This result is of extraordinary significance. Most astronomical bodies in the vast universe contain an almost infinite number of individual characteristics. Quasars are like colossal engines in the universe. Their central black holes, through brutal friction and scorching temperatures, forge an unimaginably powerful generator. To accurately describe and reconstruct such a complex object, even in a vaguely similar form, would require a vast amount of data, trillions of numbers. Stars, which seem more intuitive and understandable, actually contain an almost infinite variety of types and undergo dramatic evolution throughout their life cycles. From the supermassive first-generation stars that existed for only a few million years in the early universe to the ultra-low-mass, frozen stars expected to witness the twilight of the universe, they are all treasures in the universe's repository of possibilities. Even a seemingly simple object like the asteroid Ryugu is engraved with the unique marks and scars of its long journey through interstellar space. But black holes exhibit a completely different characteristic. The allowed solutions for black holes are strictly limited. In fact, they are completely constrained by three fundamental properties. It is astonishing that describing a black hole requires only three numbers: mass, charge, and angular momentum. That's it. No other parameters are needed. These three numbers are enough to reveal all the mysteries of a black hole. As the American physicist John Wheeler succinctly put it, a black hole has no hair. This means that every black hole in the universe can be completely described by just three fundamental parameters: mass, charge, and spin. There are no other features. But behind this mask of seeming simplicity, the formation process of a black hole contains an almost infinite number of initial possibilities. This makes one ponder: how are all these complex initial conditions ultimately simplified into these three numbers? When physicists hear the concept, a black hole has no hair, their minds immediately connect to another profound and distinct area of physics: thermodynamics, the science that studies heat, temperature, and entropy. Imagine this scene. You are sitting on a smoothly flying airplane. The cabin is filled with air at a specific temperature and pressure. We can tangibly feel these macroscopic properties, whether it's the warm airflow caressing our skin or the subtle change in cabin pressure as the plane descends. But we are completely unaware of the countless microscopic atoms that make up this mass of air. In fact, any space is filled with a huge number of molecules, constantly colliding and moving, so much so that macroscopic beings like us cannot distinguish individual atoms. When we talk about temperature in the sweltering heat, what first comes to mind is often the suffocating stuffiness. We rarely think deeply about the fact that it is the gas molecules within, dancing at a faster pace, that weave this experience of heat. Although we might vaguely perceive that the essence of heat is actually a vivid depiction of atoms in the microscopic world moving faster and carrying more energy, everyday language often stops at the surface. Black holes and a room of gas, two seemingly disparate physical systems, share a poetic simplicity. Just a few key numbers are enough to outline their essential features: the spin and charge of a black hole, the temperature and pressure of a gas. These numbers are like mysterious codes, behind which lie the magnificent landscapes of their respective internal states, containing infinite possibilities and exquisite arrangements. In the context of physics, there is an elegant concept that specifically captures this internal richness: entropy. It is like a poet skilled in calculation, counting the number of all possible microscopic states of a particular physical system. The calculation of entropy depends on the various parameters of the system. For a gas, it is the stage built by temperature and pressure. On this stage, Each specific set of parameter values corresponds to the graceful dance of countless microscopic configurations. The broader the parameter space, the richer the allowed microscopic arrangements, and the higher the system's entropy. For a gas, entropy aptly measures the infinite possibilities of molecular motion. Given a certain volume, pressure, and temperature, the gas atoms perform a dance of ever-changing motion on this three-dimensional stage. Entropy, this mysterious thermodynamic quantity, measures the number of internal microscopic states of a system. When the temperature of a gas rises, the entropy value also increases. Every increase in temperature means a slight acceleration in the speed of molecular motion and a small increase in the energy they carry. From the perspective of possible directions of motion, the paths to increasing speed are far more numerous than those to decreasing speed. Imagine when a particle's motion approaches the limit of being at rest. Its mode of motion is limited to one, complete stoppage. Can these thermodynamic concepts, applicable to gases and elastic bodies, be extended to the most inert existences in the universe, black holes? Although there are no racing atoms inside a black hole, the laws of thermodynamics still apply. Just as we can define the temperature and entropy of a gas, we can also discuss the temperature and entropy of a black hole. This major discovery can be traced back to the early 1970s, first proposed by physicist Jacob Bekenstein and later further developed and perfected by Stephen Hawking. Bekenstein was a graduate student of the famous theoretical physicist John Wheeler. In an academic discussion, Wheeler presented Bekenstein with a thought-provoking phenomenon. When hot tea and cold tea are mixed, the overall entropy of the system increases irreversibly. But if the teacup with the mixed tea is thrown into a black hole, all evidence of the mixing process will be annihilated. After the tea is swallowed by the black hole, it eventually merges into that one eternal black hole solution. This phenomenon prompted Bekenstein to question whether mixing hot and cold tea really increases the total entropy of the universe, because when the tea falls into the black hole, all the entropy it carried seems to disappear with it. This line of reasoning clearly contradicts the second law of thermodynamics, a cornerstone of physics, which asserts that the entropy of the universe must increase over time. This idea is one of the most precious insights of modern physics. The famous astrophysicist Arthur Eddington once incisively pointed out, the law that entropy always increases holds, I think, the supreme position among the laws of nature. If someone points out to you that your pet theory of the universe is in disagreement with Maxwell's equations, then so much the worse for Maxwell's equations. If it is found to be contradicted by observation, well, these experimentalists do bungle things sometimes. But if your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation. For this reason, Bekenstein proposed a revolutionary insight. Just as every cup of tea has its entropy value, when two cups of tea are mixed, the total entropy must increase. Similarly, when a cup of tea is thrown into a black hole, the total entropy of the black hole should also increase accordingly. It was this profound insight that led Bekenstein to a shocking conclusion. Black holes must indeed have entropy. This discovery was later called the Bekenstein-Hawking entropy. This was undoubtedly an extremely peculiar discovery, but what did it really mean? Since the first discovery of astrophysical black holes in the 1960s, humanity's exploration of the hottest black holes in the universe has never ceased. In this long research journey, scientists have discovered a wide variety of black holes. The most massive black holes known, such as Phoenix A** and TON 618, have masses a staggering 100 billion times that of the Sun. These behemoths reside at the centers of huge, active galaxies. As supermassive black holes, the quasar jets they release contain astonishing energy, enough to illuminate an entire galaxy. At the other end of the mass spectrum, the lightest black holes detected by scientists are those dark companions hidden in the orbits of other stars or pulsars, with masses only a few times greater than our Sun. The latest black hole candidates, PSRJ 1514-42e or the orbital companion of the red giant V723, have sparked great interest in the scientific community. These miniature black holes, although tiny in size, are a billion times hotter than distant giant stars. Although in absolute terms, their temperature is only 1/10,000th of a degree above absolute zero. This high temperature is already a relative miracle. So, where does the faint heat of these black holes come from? By the early 1970s, Bekenstein and Hawking had already determined that the entropy of a black hole should follow the laws of thermodynamics. As particles fall into a black hole, the entropy of the particles is transferred to the entropy of the black hole. In this way, the overall entropy of the universe increases, and the laws of physics seem to be satisfied. But as Hawking, with his extraordinary mind, pondered this picture more deeply, he keenly caught a problem within it. Imagine a cloud of hot gas falling into a black hole and being completely swallowed. Logically, the resulting black hole should be cold, dark, and deadly, like a mysterious abyss that can swallow everything. Nothing can escape from its interior. It is like an object at zero temperature. In other areas of physics, when hot and cold objects are mixed, the temperature of the cold object rises due to the mixing process. But with black holes, the situation is completely different. It's like a stubborn conservative, always remaining inert, its temperature constant at absolute zero. This is the essential feature of a black hole. Even light cannot escape its gravity. But just in this seemingly flawless theoretical picture, Hawking proposed a breathtakingly subversive idea. He emphasized and further deepened the concept that a black hole is a thermodynamic object with entropy. He boldly proposed that black holes not only have a temperature, but that this is by no means some mathematical analogy or a gravitational equivalent. It is the same ordinary temperature we are familiar with in our daily lives, used to describe the scorching heat of an oven, the boiling of water, and the cold and warmth of the weather. The most mysterious object in the universe is bizarrely and wonderfully connected to the temperature we perceive every day. This astonishing discovery can be traced back to the classical laws of thermodynamics of the 19th century, which closely link entropy and temperature. It states that the temperature of an object is the reciprocal of the rate of change of its entropy with respect to energy. Take a gas, for example. When extra energy is injected into it, the number of gas configurations increases accordingly. Through precise calculations, we can then derive the temperature of the gas. But the case of a black hole is completely different. The entropy of a black hole is actually determined by the area of its event horizon. In the simplest Schwarzschild solution, this entropy is proportional to the square of the black hole's mass energy. When we bring this unique relationship into the classic 19th century thermodynamic expression for temperature, a stunning result is born. A black hole must have a temperature. This property is exquisitely inversely proportional to its mass energy. Massive black holes are like cosmic iceboxes, while tiny black holes are as hot as raging flames. In our Milky Way, a typical astrophysical black hole, born from the remnants of a collapsed star, has a mass only slightly larger than the Sun, but its temperature is only about 1/100,000th of a degree above absolute zero. But according to current knowledge, a much smaller hypothetical black hole, formed by compressing a behemoth like Mount Everest to a singularity, would have its temperature soar to hundreds of billions of degrees, far exceeding the temperature limit of any known stellar core. This counterintuitive property reveals the deviation of black hole behavior from common sense. An ordinary flame starts hot, gradually cools as it releases heat, and finally ends with a faint glow in the embers. A black hole, however, is the exact opposite. It starts cold, becomes hotter as it loses energy, and finally completes its magnificent evaporation in a blazing inferno of radiation. This is the most bizarre, yet most typical, essential feature of a black hole. As we try to decipher the mystery behind this phenomenon, let's start with the most fundamental question. Why do black holes have a temperature? Hot objects radiate energy outwards. Simply place your hand near a flame or an oven, and without touching it, you can feel the scorching heat. In physical terms, heat means that an object can transfer heat to a colder object. When two objects at different temperatures come into contact, heat spontaneously flows from the hotter body to the colder body until they reach thermal equilibrium. However, the existence of black holes seems to subvert this natural law. In traditional understanding, black holes are like gluttonous beasts in the universe, only taking in and never giving out. They devour everything that falls within their event horizon, mercilessly dragging this matter towards a mysterious singularity, but never releasing anything. The name black hole comes from this. They swallow light, but emit no radiation. But the scientific discoveries of the 1970s completely changed this perception. Black holes actually have entropy, which means they are not completely black. Imagine placing your hand near a black hole with a temperature of 1000 degrees. The experience should be no different from being near an oven of the same temperature. Just as our skin can perceive the photons emitted by the oven, which strike it and transfer energy, which is then transmitted as a heat sensation to the brain via nerve signals, there must be some mechanism in the space around a black hole that allows photons to strike our skin and transfer heat. But this leads to a seemingly absurd question. Where do these photons come from? If they indeed come from the black hole, it means that actual particles must be escaping from the black hole. This is in sharp contradiction with the classic definition of a black hole as something that only takes things in and never lets them out. Do particles really escape from within a black hole? Amazingly, the answer given by science is yes. Among Stephen Hawking's many outstanding contributions to the field of physics, this discovery is undoubtedly the most important and far-reaching. The faint glow spilling from the edge of a black hole was later respectfully named Hawking radiation. Its spectral characteristics perfectly matched the theoretical predictions based on the black hole's temperature. The theory of Hawking radiation is quite mature in the academic world and has been verified through many different research paths. But the common point of all these research methods is that they are all based on the intersection of three major disciplines: gravitational physics, black hole theory, and quantum mechanics. To truly understand this wonderful phenomenon, we first need to think about Heisenberg's uncertainty principle. In the world of quantum mechanics, an absolutely still vacuum does not exist. Nothing can reach a state of complete stability, or in other words, no space can reach a state of absolute stillness and equilibrium. Imagine you are suspended at the edge of a black hole's event horizon, that insurmountable gate of destiny. With just one gentle step, you would fall into an eternal abyss of darkness. Your existence would be completely sealed within this fold of space-time. But suppose you have a starship equipped with an extraordinary engine, its immense power just enough to counteract the black hole's deadly gravity. The engine roars continuously, anchoring you firmly in this dangerous critical zone. Now, two beacons stand on your ship, one pointing towards the all-devouring gate of darkness, and the other pointing towards the vast starry sky of freedom. The light from the beacon pointing towards the event horizon, like a moth caught by the hand of fate, instantly passes through that invisible gate and is forever lost in the embrace of the black hole. The brilliance emitted by the other beacon, like a bird breaking free from its shackles, soars towards the boundless depths of the universe, eventually reaching the shore of light. This is exactly how Hawking radiation works. Heisenberg's uncertainty principle contains a profound idea. In the wonderful world of quantum mechanics, even in the coldest, emptiest vacuum, it is by no means nothing. The vacuum actually hides inherent energy and can even borrow this energy for a very short period of time. The more energy you want to borrow, the shorter the time you are allowed to borrow it. This means that in an extremely short moment, the vacuum can borrow enough energy to create a particle-antiparticle pair. Although this is just a fleeting encounter, as long as the pair of particles quickly combine and are absorbed back into the vacuum, their energy is returned as it was. This process does not violate the laws of physics or the law of conservation of energy in the slightest. Although all this seems absurd and bizarre, it is one of the key examples of the complexity of the vacuum in quantum mechanics. It seems there is no phenomenon in the world more pure and simple than this. But most importantly, the vacuum is not just an empty space stretching infinitely in all directions. We focus on the space just outside the black hole's event horizon. The black hole's incredibly powerful gravity is always ready to drag any object into its clutches across that mysterious event horizon. The vacuum, it seems, is also given an inward direction. So what magical story will unfold just outside this event horizon? When energy is borrowed from the void of the vacuum to create a pair of twin dancers, a particle and an antiparticle, for a photon, it is both the dancer and its own mirror partner, two back-to-back photons briefly appear on the uncontrolled strings. In this fleeting moment, the pair of photons begin their journey. One of them bravely crosses the event horizon, this one-way street to the singularity, forever separated, never to meet again. This situation is just like a rocket teetering on the brink of the black hole's abyss, simultaneously emitting photons both inwards and outwards. The mystery of the quantum vacuum lies here. Every time a particle or antiparticle escapes into the vast universe, its twin partner falls into the embrace of the black hole. This borrowed energy must eventually be repaid. The black hole must pay the price for this temporary gift. The final result is astonishing. The escaping particle carries away a trace of energy, and this energy comes from the black hole's own mass. Precise calculations confirmed Hawking's foresight. This process is like a fiery furnace, radiating light. Hawking radiation was thus born. These escaping photons constitute the body temperature of the black hole, revealing a subversive truth. Black holes are not eternal dark prisons. But the mysteries of the universe are endless. When enough time has passed, the black hole will eventually evaporate completely. Everything inside it will return to nothingness, leaving only a ripple in space-time to tell of its former existence. We can imagine the history a black hole experienced before its formation. Countless encyclopedias and databases continuously fell into the black hole under the influence of gravity, gradually forming a patch of darkness. As time passed, the black hole began to evaporate, and finally, a stream of gas particles poured out from where the black hole once was. So, in this process, what happened to all the information that once existed? According to Hawking's calculations, the radiation emitted by a black hole is a completely featureless thermal spectrum, containing no trace of the original information. Where did this information go? Can it be reconstructed from the details of the emitted radiation? For 20 years, this question was highly controversial in the field of ordinary quantum mechanics. One view was that the information was not lost, that perhaps black holes were not like that. Another view speculated that this unusual combination of gravity and quantum mechanics might lead to some fundamental differences. The final answer emerged from an unexpected direction. Entropy is proportional to the area of the black hole, not its volume. This discovery was the first sign of a profound and subtle idea called the holographic principle. This principle has far-reaching implications for the universe. Imagine you throw a book containing human wisdom into a deep black hole. How to preserve it in the brutal accretion disk and violent radiation waves. These details are no longer important. The key is that we can imagine the process of the book continuously falling until it reaches the core of the black hole, that mysterious and unpredictable gravitational singularity. There, all the information carried in the book will be completely crushed and turned into nothing. This raises a profound physical proposition. Is the information completely destroyed, or does it survive through some unknown mechanism? To find the answer to this puzzle, we seem to have to delve into and understand the most peculiar place in this universe, the singularity at the center of a black hole. What is the inside of a black hole really like? In the framework of quantum gravity theory, can information miraculously survive? If we could accurately record all the details of every photon escaping from the black hole through Hawking radiation, could we, in principle, reconstruct the information that was swallowed? To date, most of the theories about black holes, whether it's their existence itself, the concept of entropy, or the prediction of Hawking radiation, are still fascinating scientific ideas. Most of these ideas were formed in the late 1970s. But subsequent research revealed an even more astonishing fact. Black hole physics contains a much deeper and more bizarre truth than we initially imagined. Most importantly, black hole research has given us our first glimpse into one of the most fascinating and shocking essential features of gravity, the holographic principle. It is this holographic principle that provides us with the most exquisite theoretical framework for understanding the whereabouts of lost information in black holes. Let's first go back to Hawking's groundbreaking discovery. The mathematical expression for a black hole revealed a seemingly ordinary but revolutionary law. The entropy of a black hole is proportional to the area of its event horizon, not its volume, as traditionally expected. This discovery was like dropping a bombshell in the world of physics. Physicists had long known that the mass of a black hole is closely related to the geometric area of its event horizon. This spherically symmetric boundary of no escape imprisons all matter. For the simplest Schwarzschild black hole, the area of the event horizon is determined solely by mass. For a rotating black hole, this relationship evolves into a complex function of mass and spin rate. In 1971, Stephen Hawking proved a stunning fact. No matter what complex process it undergoes, the area of the event horizon will only increase in one direction. This perfectly matches the property of entropy never decreasing in the second law of thermodynamics. Bekenstein and Hawking keenly perceived that it was this area of the event horizon, not mass, volume, or angular momentum, that perfectly interpreted the essential property of entropy. When matter falls into a black hole, it not only increases the black hole's mass, but also brings in new information, thereby increasing the entropy inside the black hole. And when two black holes merge, the area of the event horizon of the newly formed black hole will be greater than the area of the event horizon of either of the original black holes. This phenomenon is as if the universe is silently following some profound law of information conservation. In complex slingshot systems that can extract mass and angular momentum from a black hole, the black hole's mass will decrease accordingly, but its event horizon area will increase. But why is this phenomenon surprising? As we have learned, black holes are similar to gases in some respects. Both are thermodynamic objects with temperature and entropy. Just as a hot gas can emit radiation, a hot black hole can also emit radiation. However, there is an important and subtle difference between the two. Specifically, the entropy of any object is a measure of the total number of internal structures of that object. That is, the number of ways to rearrange an inert gas while keeping its external properties unchanged. For a gas, its entropy increases as the volume of the gas increases. We can imagine a balloon at a specific pressure. While keeping that pressure constant, the larger the volume of the balloon, the more possible structures can exist inside the gas. Based on this, let's assume we divide the entire gas volume into many small cells. Each cell represents a unit of spatial volume, and each volume exists in either an on or off state. Here, on means a gas particle is located in that volume, and off means a gas particle is not in that volume. If there is only one cell, there is only one choice. If there are two cells, there are two choices. If there are 3 cells, there are two choices. If there are 100 cells, there are 100 choices. In general, the total number of structures is 2 to the power of the number of cells. So what is unique about a black hole? For a black hole, the Bekenstein-Hawking entropy depends not on the volume of the black hole's event horizon, but on its area. From our perspective of small cells, the state of each cell can be 1 or 0. This formula means that for a black hole, we can calculate the number of its internal configurations by dividing the area of the event horizon into many small cells. This technical process is similar to what we did for a gas, but the key is that we are performing the calculation on the surface of the black hole's event horizon, not its internal volume. This is the manifestation of the holographic principle. For many gravitational systems, the physical properties of the system are completely encoded on the boundary of the system. The gravitational equations inside can be rewritten or converted into a different set of equations. These equations describe a non-gravitational theory that exists only on that boundary. A gravitational system in 3-dimensional space can be equivalent to a non-gravitational system on a 2-dimensional boundary. A gravitational system in 5-dimensional space can be equivalent to a non-gravitational system on a 4-dimensional boundary. In general, a gravitational system existing in a certain number of dimensions is equivalent to a non-gravitational system existing in one less dimension than the gravitational theory. Some people might think this concept is somewhat redundant, but it is actually not. This correspondence is one of the most profound ideas in modern theoretical physics and is supported by a large number of calculations. Its core idea is that two seemingly independent mathematical theories, one a 5-dimensional gravitational theory, the other a 4-dimensional non-gravitational quantum theory, are actually the same theory, just expressed in completely different languages. In fact, This correspondence is considered an effective way to connect the previously incompatible theories of gravity and quantum mechanics. The expression for black hole entropy proposed by Hawking was like a bright lamp, illuminating the first ray of light of this profound theory. But how does holography solve the information paradox? Where did the lost information go? Holography reveals a stunning perspective to us. A gravitational system and its evolutionary process can be completely described in another, non-gravitational language. Imagine a gravitational system with a non-gravitational holographic description in which there is a black hole. In the framework of this gravitational theory, the black hole forms and eventually evaporates. We would naturally worry about the loss of information. But in another, holographic, lower-dimensional description, this process presents a completely different picture. The formation and evaporation of the black hole occur entirely in a non-gravitational context. Here, it is just a system evolving according to the ordinary laws of quantum mechanics. In such a quantum system, there are no difficulties with singularities or event horizons, and there is no problem of information loss. The information is simply preserved on the event horizon, stored in the lower dimensional boundary. But even if we are convinced that the information will ultimately be preserved, where does it reside? The most exquisite answer is perhaps that it is hidden in the subtle texture of Hawking radiation. Although we often think of black hole radiation as a stream of uncorrelated photons emitted like from an oven, this view is not entirely accurate. Instead, some physicists propose that all the radiated photons are subtly correlated and entangled, and the information that fell into the black hole is hidden in this quantum correlation. Thus, black holes are indeed one of the strangest objects in the universe. They constantly challenge our understanding of the nature of information and reality. But when a black hole forms, and before it evaporates, what is it made of? Can we truly reveal the essence of a black hole? The microscopic structure of a gas involves the positions and velocities of all the atoms that make up the gas. But discussing the analog for a black hole is a challenging question and seems difficult to verify through experimental means. To investigate the internal composition of a black hole, the rocket we imagine, equipped with advanced future technology, must first cross the black hole's event horizon. But this action would cause the rocket to never be able to return. Therefore, any knowledge it acquires cannot be transmitted to the scientists left outside. Thus, the internal structure of real black holes, wrapped in layers of event horizons light years away, is beyond our current capabilities, both practically and theoretically. However, mathematics can reach where rockets cannot. When we cannot conduct physical experiments, thought experiments and mathematical calculations become the next best option. These theoretical models, though unable to perfectly replicate the real world, can describe idealized systems that share key characteristics with reality. For this reason, some mathematical models, although idealized, can capture some of the physical properties of real black holes, and with their high degree of symmetry and controllability, they allow us to perform precise calculations under specific conditions. In 1995, Andrew Strominger and Kamran Vafa at Harvard University conducted a landmark computational study. They focused on a highly idealized five-dimensional black hole model in string theory. This mathematical construct exists in a wonderful universe with one more spatial dimension than our three-dimensional world. These special black holes not only have an extra spatial dimension, but also possess a series of unique symmetries and physical properties. These characteristics do not exist in the ordinary black holes in our familiar four-dimensional universe. Strominger and Vafa, with their outstanding mathematical skills, accurately calculated all the possible microscopic states inside these special black holes, the combinations and the possible arrangements of all the microscopic matter that constitutes the black hole. In their calculations, they involved an extended object in string theory called a D-brane. The entropy calculation result they finally obtained was in complete agreement with the black hole entropy formula proposed earlier by Hawking. This achievement was of extraordinary significance. In a simplified mathematical model that included extra dimensions and symmetries, physicists for the first time successfully explained the origin of black hole entropy from a microscopic level. But reality is always full of challenges. For real black holes like Sagittarius A** or TON 618, we still know nothing about their internal structure. We cannot determine their internal microscopic states, nor do we understand how the laws of physics on the event horizon accurately describe the internal structure of these mysterious celestial bodies. However, revolutionary theories like the holographic principle bring us hope. Perhaps one day, we will be able to glimpse the mysteries inside a black hole. Of course, this may have to wait until these most mysterious objects in the universe reveal more surprises to us at the intersection of gravitational astrophysics and quantum mechanics. For nearly 300 years since the concept of black holes was proposed, they have always been the most fascinating puzzle in the universe. To this day, that title remains well-deserved.